live in an age where telescopes have become time machines, letting us see all the way back to the beginnings of our universe. The Hubble Space Telescope and the James Webb are still giving us stunning images of nebula and galaxies by focusing on small patches of sky, capturing light that traveled billions of years to reach us. And from the ground, the Rubin Observatory is now beginning to sweep the sky repeatedly, building a moving map of the cosmos in visible light.
We're seeing a very distorted version of the universe.
The thing is, even with all that, we're still not seeing 95% of what's there. The forces that shape the universe, dark matter and dark energy, remain invisible and still not understood. So what if we sent something up that may just give us a chance to see the rest of it? Enter the Nancy Grace Roman Space Telescope, NASA's Wide Field Survey mission, targeted for launch as early as 2026. Its wide field will deliver an unprecedented flood of data, so NASA is preparing now with a simulated universe, a dress rehearsal before Roman ever opens its eye in space.
Every picture has about 2 billion photons that are coming to us from these extragalactic objects.
For us, survey means lots of data across the sky very quickly. It's delivering data for the whole community at once. So it's a different mode for NASA.
And we can take this and transform it into...
Michael Troxel and Dan Skolnick lead Duke's new space initiative, working with teams around the world to prepare for Roman's coming survey of the cosmos. One of the key projects is called Open Universe, a massive simulation of how Roman's and Rubin's surveys will see the sky, so scientists can practice with realistic data and refine their analyses before the telescope starts. Roman will sweep huge swaths of sky over about 5 years from Lagrange Point 2, about 1 million miles from Earth, near the James Webb, far above the atmosphere where the view is sharper, darker, and uninterrupted.
I mean, the Roman Space Telescope has this amazing history where it was essentially originally a military spy satellite that was sitting in a hangar and gathering dust. Someone in the military for the National Reconnaissance Office reached out to someone high up in NASA and say, hey, any chance that you guys would be interested in this satellite? Instead of kind of looking down on Earth, you look up at the stars. So we said yes and have been refurbishing it, putting new instruments on, and that is kind of what we're now using. That's the Roman Space Telescope.
Roman will take sweeping infrared pictures of a universe, seeing light in waves our eyes can't. And in those waves, it will track how that light shifts and how gravity bends it across space.
And then we take every object in that universe and we simulate all the photons that are going to go through the universe, around all the structure, the galaxies and clusters of galaxies, the stars in the Milky Way, and propagate those photons through this simulated Roman Space Telescope instrument that we build in our code to basically build a three-dimensional map of the structure in the universe.
NASA started this years ago, building a simulation of our nearest neighbor, Andromeda, based on Hubble data. When Hubble built its portrait of Andromeda, it did it piece by piece, more than 400 separate frames over 3 years. But Roman could cover that same galaxy in just 2 wide-field shots, and that sweeping view comes from Roman's wide-field camera, made up of 18 separate detectors working together like a single giant mosaic. With that reach, Roman won't just map galaxies. Researchers hope it will also help reveal what dark matter and dark energy are doing out there. Troxel's approach, called weak gravitational lensing, uses tiny distortions in galactic shapes to trace the invisible mass in between.
If you think about a pool on a hot summer day, and you look down at the bottom of the pool, you'll notice there are all these speckles and waves of light, bright parts and dark parts. And this is really, really similar to the effect that gravity has on how large-scale structure appears to us. Where there's a lot of mass, you get photons that curve around the mass and converge, produce a brighter image. And when there's not much mass, the photons curve away from that area of space. And so those waves of light that you see on the bottom of a pool are kind of like the measurements that we're making of these faraway objects in the universe.
First, they build the universe in a computer, galaxies, stars, all of it. Then they follow the photons to predict what the telescope would record when it starts its work, tracing how that light travels through the mirrors down to the electronic sensor that captures the final image. How do you build a simulated universe? I mean, what are we looking at here?
Yeah, so these are what you would see if you looked at the night sky with your eye. You just see the things that are nearby, these stars, which make up objects in our Milky Way. We can take this image and change the scaling, though, to see what the Roman Space Telescope will see. And suddenly, you see all of the galaxies that are in the bat. In this image, there's something like 2,000 galaxies.
Roman won't be working alone. It has a partner. Its data is complemented by the Earth-based telescope, the Vera C. Rubin, completed in 2025. Rubin will scan about half the sky, again and again, catching change as it happens, exploding stars, moving objects, subtle shifts across the cosmos.
The Rubin Observatory and the Roman Space Telescope are highly complementary. That is, we can do a lot more with them together than we can with each individually. We can see optical wavelengths like our eyes with the Rubin Observatory, but we can see further into the infrared with the Roman Space Telescope, so we can learn more about the objects that we're observing. And the two missions are designed to overlap, so that we get the same data from both for the same set of objects.
But we do see diffraction spikes.
Skolnick is studying not gravitational lensing, but is focusing in on another signal Roman will use to track how the universe has changed.
I will use the Roman Space Telescope to find supernovae exploding billions of light years away. And from each supernova, we get a snapshot of kind of what the universe looked like at that time.
Roman isn't just taking pictures, it's measuring distance across billions of light years.
So the example I like to give is, it's like if you get the same light bulbs from Home Depot, and you know they have the same wattage from the same factory, and you see two light bulbs in your room and one looks brighter than the other, you could tell, oh, this one must be this much closer than the other. But you need to know that those light bulbs are exactly the same.
It's a simple comparison, but the stakes are enormous.
If on the supernova side or on the lensing side we see something weird about the universe, we see something that's doesn't fit in our model, first we would say, well, extraordinary claims require extraordinary evidence. That if you're going to say our model is broken, the universe is weird, you really want to be sure, and then you want multiple different ways of measuring it to be confident.
That's the real promise of Roman, not just sharper images, but maybe some answers as well.
And who knows what we're going to see? When you open the door and look somewhere for the first time, that's where we learn about the universe. That's where we learn about physics. And that's really the exciting potential for the Roman Space Telescope. The things that we're not even aware that we don't know yet that we're going to find.
Thanks for watching. If you like science stories like this, click subscribe now for more Science-y and PBS North Carolina.